so that we are at the same page. And I'll request everyone to be interactive. Anywhere you are having any doubt, it might sound very silly. So please pipe up and all of us will discuss that so that we are having the same understanding. With that, may I start? Yeah.
Yes.
Yeah. Thank you. Thank you so much. Yeah. So I will share my screen. I will open I need to comment. I will open the lectures also so that if we have to take some reference, then we can open that. So we are going to MLOps, GenAI week 1. So this week 1, then we go to week 2, and here is the week 2. So it will open. Okay. So basically in the week 1, what professor covered that what is the intuition? That, for example, we have got some data, and data is coming, for example, x1, x2, and it is coming up to xn. And this data, this we know that this is coming, first of all of these data points, they are IIDs. It means they are identical, independent, distributed. But we know that they are coming from some distribution, P of x, but we don't know that distribution. Okay. So is what is the goal? Goal is, first of all, to estimate this distribution, estimate this distribution. And second goal is number one. Number two is to sample from this distribution, okay, from this. So we have got some data points. We know that they are IDs. They belong to some distribution, but we don't know what the distribution. So we have to estimate this distribution, and thereafter we have to sample from this. For example, that now we have to produce some more data points from this distribution. Okay. Now, the how to approach that. So we know that any neural network, we know from our deep learning course, that any neural network is capable of approximating any function, any function, any function, and this comes from universal approximation theorem. So if you remember from your deep learning course, we used to make that that if there is a function, then we make towers, okay? And then in 2D, in 3D, we went to 3D towers. And the idea was that only that if there is any function, any neural network is capable of approximating that function. Is that clear with everyone? Any question in anybody's mind? Okay. So I take it that that is clear. So how to approach this problem, that we have got these data points. So now we say that we have got some function, and we call, for example, this is known as zz or z theta of z, and it gives me some outputs, for example, x tilde, and z belongs to any distribution which is a Gaussian distribution with mean 0 and variance identical. So if we take this neural network, and we know that this neural network is capable of approximating any distribution, then by taking this and by refining this, we can bring this, for example, and its distribution we call as p theta of x, where theta is the parameters of z theta z. So what do we do to estimate probably the distribution of x? So we make a divergence metric. So divergence metric we call it as df, and it is denoted as px by p theta. Just give me a minute, please. हाँ यादव, जय हिंद यादव. वो तो मैंने जमा करा दिया दोस्त वहां पे सैफर सेक्शन में उसी दिन. हाँ जी कर लीजिए. ठीक है, थैंक यू जय. Okay, sorry, I had a call from my office. So what do we do? That we make a divergence matrix. So this divergence matrix, you can think of like this, that there is one px of x, and we have got this p theta of x. So here we have got the data points. This is the distribution. This is the distribution coming from the neural network. So we want to, what do we want to do? We want to minimize the distance between px and x and p theta x, so that we know that now that p theta x is replicating pxx, and now using this p theta x, we can sample. Okay. So this divergence matrix is defined as df of px of p theta is defined as integral over x p theta of x and some function of which is pxx over p theta x, and like an integral dx. So this is the one divergence matrix we have to find. So objective is to find r min theta, which minimizes this df px and p theta. Is this clear with everybody till here?
Can you mention it one more time? Why are we finding this?
So what we are finding, so again, I will, at the cost of repetition, what we will do, for example, I'll give you one practical example. Some data point is coming 1, 3, 9, 17, 25, 39. Some data point is the data points are coming, and for example, here is 107. Now we know that this is coming from some distribution or from some function, and all of them, they are IIDs, independent and identical distributed. So they are coming from some distribution px of x. So just to give you an example, that they might be coming from function of, for example, y is equal to x square plus 1. Is that okay? But we don't know what is pxx. So
Yeah.
now we want to sample. First of all, we have to estimate this pxx, and then we have to generate some data points from this. Okay. So for example, what will be the, for example, some other data point. So now the intuition is that from deep learning, we know that whatever is a function might look like this. Okay. The function might look like this. But we know that our neural networks are capable of approximating any function. This we have studied in our deep learning.
Yeah.
Okay. So what do? We say that we are having one neural network. So some function, for example, z theta of z, it is giving some x tilde, and its input is z belonging to Gaussian distribution 0 and identical. Okay. Now I start comparing this neural network. So I initialize, like we used to do in deep learning and large language models, that we initialize some weights, and thereafter we start comparing them. So our idea is to bring down this divergence matrix which is there, px of x and this p theta of x. We have to minimize this divergence matrix. Then only this neural network will be able to estimate px of x. Is that okay?
Yeah.
Okay. Okay. So that is the idea. So we have to find this minimum parameters theta argmin of df of this px and p theta. So this is our objective. Okay. Objective is this. Till now, this is clear with everyone?
So once we find this, we'll be able to estimate that distribution, right?
Yes, yes. So this is the first step to understand, and thereafter we will keep on graduating.
Yeah.
Okay. Now, so what was the DFF? So now my objective becomes that R min theta, and my DF was integral of x, p theta of x, and some function of pxx over p theta of x over dx. So this is my objective now. It becomes okay. Now,
Yeah.
so now we will take help to solve this. We will take help of statistics. In the statistics, we know that if we have got two distributions or one function and one distribution, then we can find the integral. So if, for example, there is a function called, this is a hx, and there is some function of, or there is a distribution of uh, px. So this is a function and this is a distribution and this is over x. So this can be approximated by using expected h of x over px. So this is given by our statistics, and this comes from, if I'm not wrong, large number theorem. And this is very, very similar. We had studied the similar concept if you go to your MLF foundation course. So this was not covered in this exact form, but the meaning was that only. So here, see, if we have got one function, we have got one distribution. This is one function, this is one distribution. So can we use this to this? Can anybody tell me? Can we do it or can't we do it? Okay, so I'll take this silence as no. So we cannot do this because this function which is there, this function is comprising of both px and p theta. Okay, so before we go further, I will cover certain characteristics of this df and this function. So df, I have mentioned, it is integral over x, p theta over x, and f of px distribution and p theta distribution dx. So there are some characteristics of this divergence matrix. Number one, the minimum value of this df is always 0. So it will be always greater than equal to 0. Because the matrix, the difference between px and p theta x cannot be in negative. So this is one property. Second property is of this function. The function which is there. So this, if I call as function u, which is equal to function of pxx and p theta x. So this is a convex function, number one. This is a convex function. Number two, the value of this function pxx over p theta x will become 0 if pxx is equal to p theta x. Okay, so this we can understand intuitively also, that if my p theta x, that neural network which is giving me, if it is estimating pxx accurately, perfectly, then this function will give me a value of 0. Third is, from the examination point of view, you have to read that it has to be at least semi-left continuous. So this you can study, you can Google, and you can find out why this is the, what is the meaning of semi-left continuous. Can we go ahead again now? I hope everything is clear till now. Anybody, any doubt, please pipe up. We can cover it again and again because these are the basics on which everything is built up. Pooja?
Yes, now it's clear.
Okay. Okay, now, very nice. Okay, so now see, now we have reached a stage where we have to find R min of theta, and this is p theta of x, and some function of p theta, pxx and p theta x dx. We have some knowledge. Knowledge is that if we have hx and some distribution pxx. So then this can be written as expected of hx over px. So this is come from statistics, but this cannot be used. This knowledge of two cannot be used in one, because this function is comprising of both pxx and p theta x, whereas here it is only pxx. Okay, so how what do we use? So we use something called conjugates. Okay, so what is a conjugate? That if we have got a convex function, if we have a convex function fu, then we can write that its conjugate f star t will be equal to sup num, which is known as here ut minus f of u, and this domain will be the t domain will be of domain of u. Okay, so this is the first conjugate. So the conjugate meaning is what? That if you have got a convex function, so convex function looks like this. So at any point, for example, at u, you write make linear approximations, and whatever is the sup num of that gives you the conjugate. So it is an approximation. So if you see, this is a linear line. If you draw it, okay, you can further read it. The second property which you will use, that if we take conjugate of conjugate, that f star t, and we take conjugate of this, then it gives the original function fu, and this fu is always the conjugate to conjugate is, now it will become sup num. Now here u will be domain of t, this will become tu minus f star t. Okay, so this is first conjugate, this is the second conjugate, and when you take the second conjugate comes to the same function from where we started, and this is given by this. Is this okay with everyone?
Yeah.
Okay. So now we will use this property for our df. So df we had defined as integral of x, p theta of x, some function of pxx over p theta of x and dx. So let's take that your function u which is there. So in this function of u, take u is equal to pxx over p theta x. Okay, so then from this 3, we can write down dff is equal to x, and this sup which is there, it is also written as max. So this will become now p theta of x. Now this function pxx will convert to this second conjugate. So you can write down this as sup max u belonging to t and tu. So it will become t into pxx over p theta of x minus f star t. Is this okay with everyone? This step?
What did you do in the last step? Can you explain one more time?
Okay, just hold on. So what I did, just will explain. So if I take, for example, function f of pxx over p theta x, this is a convex function. So if I take its first conjugate, let's say it is fu. Okay, so its first conjugate will become f star t will become sup max ut. Now u is pxx, pxx over p theta x into t minus function of u will become same, pxx over p theta of x. Sorry, in this function. So this is like this. Is this okay? First conjugate is okay?
Yeah.
Okay. Now when you take second conjugate, f star t, and you take conjugate, so it becomes equal to, just give me a minute, somebody's at the door. Okay, I'm back. Okay, so when you take the second conjugate, now we know second conjugate becomes equal to fu, and this will become now tu. So this becomes t into px of x over p theta of x minus f star of t, and this will become sub max, and here u will belong to domain of t. So here in this one, I have replaced this function pxx over p theta x by this. Is this okay?
What have you replaced?
This pxx over p theta x, which is there, I have replaced by this.
Okay.
Okay. So your df, now there is another, I will come to that. First, let me write. So df becomes integral of x, p theta of x, and you write full this. So max u belonging to t into pxx over p theta of x minus f star t, close down this, and dx. So is this okay? This one?
Yeah.
Okay. Now, there is another property of the conjugates, that this initial, this function which is there, this conjugate to conjugate, it is always greater than equal to the first one. So this can be written as df greater than equal to, and you take this max and sup outside. So this will become sup u belonging to t, p theta of x. Now you open this, and this t becomes now t of x, and this will become pxx p theta x minus p theta x into f star t and whole of dx. Okay, and this will also become tx. Okay, so here now this df can be written down. Now you can break down these two integrals as sup u belonging to t, or here they write, okay, some t comes. So this will become p theta will cancel out. So this will become tx pxx minus integral of p theta of x f star of dx, dx and dx. So now we had covered that statistics one. Now we have got one function, we have got one distribution, and one function. So now using that statistics one, now we can write down that df will be greater than equal to, you can write down this sub max. So this will become now estimate of tx over p of x, or write down x, minus expected of function star tx. So you can write down this t of x, function of f star of tx over theta. So this is the one we are trying to achieve. This is the outcome where week 1 had finished. Shall I cover all the steps again and again for all of you? What we have done? What all properties we have used till now?
Yes,
Yeah,
please.
that will be good.
Okay. So again, just to revise, and what I feel that week 2 maybe we will cover again maybe next week. So week 2 and week 3, because the concepts are becoming slightly heavier. So what we started, we said we have got some data points x1, x2 up to xn. Now these data points are coming. They are the IIDs, and they are coming from some distribution of x. We don't know that distribution. Objective is to estimate this pxx and sample from it. Okay. So what did we do? We utilized the property of neural networks, that any neural network can approximate any function. So what did we do? We made a neural network g of theta z, and it gives x tilde, and z belongs to a Gaussian distribution 0 and I. So this x tilde, we call this distribution as p theta of x. So now to estimate pxx with the help of p theta x, we define a divergence matrix which is denoted by this p theta of x. And what do we do? Our objective becomes now to minimize the parameters of this p theta, and we of df px over p theta. Okay, so these are the steps we have taken. And then we define df is equal to integral over x p theta of x over some function of pxx over p theta x. Okay, so we have to solve this. So this is known as f divergence for the definition. Now I covered some properties of f divergence. First of all, the df is always greater than equal to 0. Okay, and when px distribution is equal to p theta of x, then df becomes 0. Then the function, this function properties, it is a convex function. It is equal to 0 when pxx is equal to p theta x, and it has to be at least left semi left continuous. Okay, so these are the properties. Now to solve this part, so I'll copy from here. Now to solve this part, we took help from statistics. So statistics says that without knowing the distribution, if we know only the samples from the two distributions, then we can sample from them. So statistics says that integral over x, and there is a distribution, and then there is a function, for example, h of x, p theta x, h of x is a function, this is a distribution. So this can be easily found out by expected hx over this x. So, but this we cannot use it here because this function has got both pxx and p theta x. So to use this, what we did, we took help of conjugates. So conjugate says that your if f of u is a convex function, then it's conjugate to conjugate, that it becomes fu only, and it is greater than equal to sup max tu minus f star of t, where f star t is the first conjugate, and this u belongs to domain of t. So with the help of this, what we did, we wrote this function pxx p theta x as fu, and then we got that df will be greater than equal to integral of p theta of x, and we wrote down this entire thing here with u is equal to pxx over p theta x. So we can write down this as sub max u belonging to t into pxx over p theta x minus f star t dx. Here I forgot in dx. So when you open this, so this will become df greater than equal to the sup and max comes outside belong to t, and p theta cancel out. So this will become p of x pxx minus p theta of x into f star of tx, and here dx and here dx. Now this two things which are there, now using the statistics, we know that we can find out this. So this becomes df greater than equal to, so this is a function, this is a distribution, so this will become expected of tx over x minus, this is a function, this is a distribution, f star t of x over theta. Is this clear? So this was the finish of week 1. Is this clear now with everyone?
Yeah.
Okay. Okay. So what I feel today that we should stop it at this. I will request all of you just follow on, just Google some things, right? Try to find out what are the meanings of conjugates. Okay. And these steps, okay, then you will come to this step that how we have got this here. If you want, I can start week 2 also. But personally, I feel that you please get this clear in your mind, how we have reached here. And thereafter, we will start for week 2. Okay. Is that okay? Any question from anyone? Aditya? Okay. Sure. Thank you. Hi, Garima. Good evening. Okay. So, can we call it off then? Anybody wants to ask anything?
Just a separate question.
Yeah.
Have you worked on like I'm not sure what is required, but have you worked on the week 2 for MLOps?
Yes, I have
Like
okay,
the video.
submitted it. So, okay. So today agenda was to cover week 2 ML ops also. So I will just give you how to approach that ML ops. Okay, week 2. So week 2 ML ops, basically the learning lesson was to how to use DCV, that is data controlled version, for tracking your data versions. Is this okay? Hello? Is this clear? The objective? Hi, good evening. No, no problem. बताओ अपने. Okay, okay. Yeah, okay. Oh, yeah, sure. So Puneet, presently I'm taking a revision session for this GenAI and ML ops. So another, yeah, yeah, sure. Yeah, yeah, yeah. No problem. Thank you so much for calling. Yeah, and why don't you join me today? Uh, I'll give you a call. I'll tell you everything. Actually, my next 2 days are slightly busy. Yeah. Okay. Yeah. Bye, Puneet. Thank you. Bye. Buddy. Hey, sorry. Am I audible? Can somebody give me thumbs up?
Yeah.
Okay. So how to approach this problem, Surupi? So what do? You make a Git में make a repo. Okay. So you know how to make a repo. So you can use what you can use. You can use Git desktop. Okay, and from there you can make a repo. And in that repo, what do? You keep iris.csv inside the data folder. Make one folder called data. Keep iris.csv. Second, then you make the requirements.txt. And then third, you can make a train.py. So train.py is the same code which is there in your week one. You read the data, then you train, test, and all that. Okay, and you are making a model. So these three things you can keep in your repo. Okay. Now, how to we have to demonstrate now on the week two, demonstrate DCV, how to use DCV. Okay. So what do? You go to your cloud account, Google Cloud. Okay. Open your Cloud Shell. Okay. In Cloud Shell, now make a directory. Make directory something, MLOps week 2. MLOps week 2, for example. Now in this MLOps week 2, now you use अपना git clone and the URL जो आपका है. This everybody is aware? Or shall I explain this? Surupi, can you do this?
This is like opening the terminal in the
Yeah.
GCP, right? Yeah.
Yes. Okay. I have actually submitted my assignment. Otherwise, I would have shown you like this also.
You mentioned to make the repository in Git. So, is that like separate from like do we use our student ID to make up GitHub repository?
No, that is not necessary. That is not necessary. Just make your repository which is there. So here is my repository. I'll just show you my repository. This is my Git. Okay. So what I've done, see, I have got this data. This is my data. So here I have got my arrays.csv. So here is my arrays.csv. Is that okay? And
Yeah.
then I got my requirements.txt. So all basic sklearn, pandas, numpy, matplotlib is there. Then I have got my main.py, and here is my code. Okay, it's the same code which is there to train your model.
Okay.
Okay. Now with this, when you go to your now I'm for this. Now this is in my student Git account.
Yeah.
But for my that I'm using my personal account. So here I'll show you. Window. So here my Git will come. Okay. So in the Git, in the Cloud Shell, okay, what you'll do. It's opening. So you have to open this. It is initializing.
Yeah.
So you open the Cloud Shell. Okay. So already see this terminal is on. Okay. So here again now you have to do all this. So I'll give you the steps. Okay, all the steps. Okay. So you make one new directory MLOps week 2. Then you do git clone and you import your repository here. Then you make your virtual environment Python 3 am VNV and you give the name, for example, .vnv. Then you activate this virtual environment by saying source and .vnv, which is the name of this bin activate. And now what you do here, now you pip install all your requirements or requirements.txt. Okay. Now these are the standard steps which we have done in our deep learning also. And now, in the Mat2 project, we used to do this. Now you have to install DCV. Pip install DCV. Okay. Now, once you have done this pip install DCV, now I have forgotten a step here. Git clone URL, and then you go to your repo. You can see your repo by doing the ls. So whatever the name will come, you have to go to your this. So for example, my repo name was MLOps. So I go to cd MLOps and thereafter I do this. Now you pip install DCV and then you have to initialize DCV. So you do DCV init. So as soon as you will do DCV init, two files will open. You can do check ls again. So you will find DCV dot ignore, and there will be one more file dot DCV, something like this. Now it means now your DCV is tracking your data now. It will start. And now to the DCV, you add your data. So DCV add and data dot iris dot CSV. So now what you have told DCV that you start tracking now this data. Okay. And now for the first iteration, now you have added this data, you just run Python Python 3, and you run your main.py. So what is happening? Your machine learning code which was there. So your machine learning code, okay, this will run, and your model has got now fitted on the data, original data, iris.csv, and it has got some 150 rows. Now what do you do to demonstrate that your DCV is tracking? In the second, what do you do? You change, or you can delete last 20 rows of iris.csv, and this you have to do from Cloud Shell. So you can find the command from system commands we used to do, or you can ask the chat GPT. It will give you a command by which now your 20 rows will be deleted. Again, you okay, before this, you have to do the git commit. Here you have run, and you have to do git add and git commit. So here you will git add your files which are there, and then you do git commit. And when you will do the git commit, it will ask you username, your email ID. So that you have to give, and then you have to use git tag. So you have to use git tag and give a tag, for example, v0. So with this, your first iteration is complete. In the second iteration, now you delete some data, and again do DCV add data.iris.csv. Again run the file Python main.py. Again do git add files. Again you do git commit. Again you do git tag, and this time git tag v1. And now how can you check that your DCV is tracking your data? So what you can do git checkout v0 and DCV checkout. Okay. And now when you do, you can find like LSLIAH, and you can find the data. So here it will give you some data size different. And when you will do the same for v1, you will get the data of different size. So by doing this, you have demonstrated that your DCV is tracking the data. Is that okay with everyone?
Yeah.
Okay. So just follow these steps, and it is just the beginning. I have not even started week 3, but week 2 we have just to demonstrate that how we can use DCV. And I had asked a question to the instructor during yesterday's live session. In fact, the GitHub also tracks the data, but to track big data, DCV is the best tool. So we have to learn, and the intent of week 2 module was to teach us how to use DCV to track that. Okay. So with this, I have finished. If there is any question, query, or any discussion, we can have that. Or can we call it a day? Yeah. Okay. Thank you so much. Thank you everyone for joining. Thank you so much. Have a very nice day. And how many of you are coming?
Thank you so much.
Yeah, anytime. How many of you are coming to Paradox? Okay. Chalo. Okay, bye bye. Have a nice day. Take care. Bye bye.